All right. So we are in Tuesday, week 6. This, um, after this lesson, we're officially halfway through the term. We're more than halfway through the material. We have chapters 7, 8, 9, and 10 left. So we have 4 chapters left. This chapter, chapter 7, is the shortest. I think tonight is the shortest lesson of the entire term. And if I put 7.1 and 7.2 together, it would be pretty long. And so I split them up, and you guys just get a nice short night tonight, the nice short lesson. There's not a whole lot of math tonight. Today's a foundational. 7.1 is kind of a foundational thing. 7.2 is when we're going to do the math. My other computer now is doing something wonky. Okay. So today is, as I said, it's like the foundational stuff. We're learning kind of a little bit of new vocabulary, just kind of adding on to what we've already done. And so, yeah, super short lesson. I'll give you a time to go out in the 80-degree weather and enjoy that sun for a little bit before it's time to wind down for the night. So tonight we are going to talk about uniform probability distribution. That's not very long. We've done it a little bit. We've talked about it a little bit, and we're going to, dive into that just for a moment. Then we're going to talk about the graph of the normal curve. It's going to look super familiar. I've kind of talked about it a little bit to kind of foreshadow. We're going to talk about the properties of the normal curve. We're going to talk about the what part area plays in the normal density function. So it's going to be super quick. There's only 18 slides. We move through them pretty fast. I would be really surprised if we go past maybe 6:15 at the latest. So as I said, this is a pretty quick lesson. And then we'll finish up chapter 7 on Thursday, and that'll be the last of the material for test number 2. I'm hoping you all noticed the review document in week 6. I'm going to pop over there real quick. So in week 6, if you go down there, where is it? Scroll, please. If you're in week 6, down here at the bottom, there's test 2 review right here. And there's a document, and it does not have chapter 5 in it. It only has 6 and 7. So for chapter 5, you will want to just go back into the old assignments, and you can just go through those in review. So you can, assignments that are closed, you can go back and you can do them in practice mode. You can do those assignments as much as you want. So do that for chapter 5, and then chapter 6 and 7, I have that review assignment. The assignment is not, it's optional. It is not an assignment that gives you a grade. So that's that, and let's jump in. Okay. So for uniform probability distribution, you may recall when I showed you the graph of it, it looks like a rectangle. And we did something very similar to this, I believe, earlier. So your friend is always late. We all have a friend like that. And if you don't, you're probably that friend. So they could either be 0 minutes late or 30 minutes late or anywhere in between, and they're equally as likely to be any of those. They're equally likely to be 3 or 4 minutes late as they are to be 25 to 26 minutes late. So equally likely to be any of those. Well, our random variable X is going to be any value between 0 and 30. So when we set this up, I'm going to show you this uniform probability distribution. Well, I'm going to talk about review. Remember our probability distribution, and it's the same thing as the probability density. The total area is going to be 1. It's the same thing as all of our probabilities added up, equal to 1. So when we see it as a graph, the area under the graph is going to equal 1, or 100%. The height of the graph is going to be greater than or equal to 1. Every little bit of the height represents that probability, because I have 1/30th of a chance of being 5 minutes late as I am, and 1/30th of a chance of being 25 minutes late, or your friend does. So the height of my graph is going to be the probability, and the entire area under the graph is going to be equal to 1. So here's my graph. Took a picture of this out of your book, so that's why it looks kind of weird. So since I have 1/30th of a chance of being any minutes, This right here, if this was, this look like about 10 minutes. Since I have a 1/30th of a chance, because that's 1 minute out of the 30 minutes, 1/30th of a chance of being 10 minutes late. So that's why the height of this is the probability of that. Get out of that. So if I took the 30 minutes that I have here, multiply them by 1/30th, that area equals 1 because 1 or 100% is the entire graph. So this is just the area represented as a graph, and we're going to be seeing this. Um, we're going to be seeing this area and this probability model over and over and over again, and I'm going to kind of make that connection tonight. So take a look here. So we want to know the probability that my friend is going to be between 10 and 20 minutes late. So this chunk right here of my graph is 10 to 20 minutes late. And the way that I can calculate that probability is I take the number of minutes. So I have 10 minutes, and it's 1/30th for each of those minutes. 1/30th of a chance for each of those minutes. So that would be 10 over 30, which is 1/3. So this graph right there, that rectangle, has an area of 1/3. You can see that it is 1/3 of that entire rectangle is shaded, and it's a 1/3 probability of being between 10 and 20 minutes late. Hope that makes sense. So for letter B, we know that there's a 20% probability my friend is going to arrive between a certain number of minutes. So here, this was my number of minutes. And this is the height. And then I get the probability. So now I can take the math and do it this way. So I don't know the number of minutes, so I'm just going to call that X times 1/30th is going to be a 0.2 probability. I just converted that 20% to a decimal. So this is just your basic solving an equation. I can get rid of that fraction by multiplying everything times 30. So I can multiply both sides of my equation by 30. Basic algebra. And I know I can do this in my head, but I really don't trust myself. So X equals 6 because 30 times 0.2 is 6. So therefore, there's a 20% chance or 20% probability my friend is going to arrive between the next 6 minutes. Questions? So this is the super simplified area model. Since it's using the uniform distribution, it's a little bit easier than when we have things that aren't just a uniform distribution. Rectangles, we can find the area of rectangles all day long. But sometimes things start looking a little bit different. So I'm going to go to my next page unless somebody needs me to stop. We're good? All right. So this right here is our normal curve. You've seen me to refer to it as the bell curve. It is a symmetric curve. It's normal. It is the normal distribution. This is the desired distribution. When things follow a normal distribution, there's a ton of different math that we can do with it. All of our analysis methods work really well when we have a normal distribution. There's some of them that we can't use with uniform or with skewed data, but thankfully, in the next few weeks, you'll learn about what to do if our data is skewed or if it's a uniform distribution and how to make it normal. But when it comes to us normal, it is so much easier to work with. And it's just this lovely bell shape right here. And this is a nice histogram with this lovely bell shape. And I'm not going to really get into inflection points a whole lot. What inflection points, they're very calculus-y. If you're in calculus, you know what an inflection point is. If you are not in calculus, it doesn't even matter. But our normal distribution looks like this. Our mean is going to be smack dab in the middle. We've talked about kind of the shape of this when we're dealing with our empirical rule. This week, we're going to get a little bit more detailed and more specific. Because remember, the empirical rule says that approximately 95% of our data is within 2 standard deviations of the mean. It is not exactly 95%. So we're going to be calculating exact probabilities rather than using our approximates with the empirical rule. We're going to do all those calculations tomorrow or Tuesday, Thursday, whatever day that is, whatever the day the next class is. That's when we're going to do those. All right. So our normal distribution does not always look nice and perfect like this one. I mean, this one is pretty standard. Sometimes it's taller, sometimes it's shorter, sometimes it's more spread out. It depends on what the standard deviation is. Sometimes it's centered around 0, sometimes it's off to the side. It has different values. It still can be normal as long as 50% of my data, approximately 50% of my data is above the mean and approximately 50% is below the mean. And we have this, the mode is right there in the middle. We have this nice distribution like this. As long as it's bell-shaped, even if it's a long skinny bell like this one, it's still a normal curve. They don't all look exactly the same. They have similar characteristics, but depending on my standard deviation, this is the way it is. As long as my mean and my median are really close to each other, it's going to be a nice, beautiful bell curve, and it's going to be lovely like this. Okay, these are our properties of our normal density curve. It's going to be symmetric about the mean. The mean, median, and mode are all going to be basically equal to each other, really super close to each other. So you're going to have that nice, even that nice peak in the middle because the area under the curve is 1. So the area to the right of my mean is going to be about half. The area to the left of my mean is going to be about half. This is all kind of stuff that we've talked about before. We just didn't refer to it as area. We just talked about how much data, but the data is basically in that area. It's kind of just hovering in there. You're not going to be asked to give this back to me. I'm not going to ask you this vocabulary. It's just kind of giving you an idea. So as we get super large and super small, so as we go this way on my x-axis and this way on the x-axis, it's going to get closer and closer and closer to that x-axis, but it's never going to touch it. I don't know if you guys remember from any other math classes the word asymptote. An asymptote is a line that a graph gets super, super close to, but it never touches. And that's basically what the x-axis is. It's an asymptote. So the graph will get closer and closer and closer, but it'll never touch it. That's how we can get outliers. Like I remember we were talking about the basketball players and they had z-scores of like 4 point something. Because it never actually touches the graph, we can have some data values way out there. The empirical rule still applies, but it's all approximate. So about 68% of the area is within 1 standard deviation. About 95% is within 2 standard deviations, and 99.7 is within 3 standard deviations. This all stays. It's all, and it's just the area. So 68% of my area is within 1 standard deviation, et cetera, et cetera. And it's approximate, it's not exact. Once we start using our fancy calculator functions and our z-tables, you'll see it's pretty close, but not exactly 60%, not exactly 95%, but it's really close. I don't remember what the number is, but it's really close. Okay. You've seen this before. This is just our lovely empirical rule, but here we're kind of more talking about area, but it's the same thing. It's just our same picture we've drawn 1,000 times, or you put in a sleeve and drew on with a dry erase marker. It's so pretty. So pretty. I love the normal curve. All right. We're going to talk about 2-year-old males. So the data on the next slide represent a sample of 50 2-year-old males. We're going to take a look at a histogram. And we're going to talk about whether or not it is normally distributed by looking at the histogram. So let's take a look. Okay, you don't have to do anything with this data. This is just my data. Okay, here's my histogram of 2-year-old males. My class width is about 1. It starts at 31.5, goes all the way up to 41.5. If I can draw a bell over this. It's not a perfect bell, but I can draw a bell over that. I wonder if I can stretch this. I don't think so. I might be able to because I wanted it to go all the way to the top. I don't think I can do that. It's still there, whatever. Okay, so it looks to me like it is pretty much normally distributed. There might be a very slight skew, but it's definitely not enough for me to say it's not normal. And we don't deal in absolutes. So if a slight skew is not going to throw us off, as long as it is mostly or approximately normal, we're going to call it good, as long as it's pretty close. I've got some tools that you're going to use later on that are going to help you really see whether or not it's normal. But for now, we're just going to look at this and say, yeah, that looks normal. So when we were talking about the area. So I have all of these rectangles in my curve. And in order to find the probability that I would randomly choose a 2-year-old male that's between 34.5 and 35.5 inches tall, I can just find the area. I can just find the area of this rectangle, which I don't have my pen on. I can just find the area of this rectangle, and it's going to give me the approximate probability that of randomly choosing a 2-year-old male between those heights. Now, we're normal approximately, and this is slightly out of the normal line, but it's going to give me a pretty close estimation of how of my probability here. I could just take this because this width is 1 and multiply it by the height, which is about zero point 0.2. So it looks like we have about a 20% chance of choosing randomly choosing a 2-year-old male between those heights. We have some more precise methods, but not yet. We're going to get there. But this is basically what area does for us. I'm just trying to get you to be able to picture what's happening. Any questions so far? Are we doing good? Just information here so far, but if you have questions, feel free. And literally, we have 3 slides left, and it's not even 6 o'clock yet. Man, I need to slow down. All right. So area under normal curve. Okay, so these are the 2 different things that the area under the curve can represent. We have 2 different things. First, it could be a proportion. It could be the proportion of a population with whatever characteristic we describe. So, for example, going back here, I could say approximately 20% of my population is between 20% of 2-year-old males are between 34.5 and 35.5 inches tall. So I could use that as a proportion. The other is a probability. The probability we would a randomly selected individual from that population will have that characteristic. I already used this one. So the probability that a randomly selected male that I pulled from, I don't even know what the population is, but if I randomly chose a 2-year-old male, it's a 20% probability that they would be between 34.5 and 35.5 inches tall. So those are the 2 things. It's either the proportion of the whole population or the probability of randomly selecting one. So those are the 2 different ways that we can use this. And you're going to, my open math will be pretty clear about which one they're looking for. And I don't think that you have to type out any conclusions in my open math. You might have to, I can't remember, but I don't think you have to. All right, so let's talk about a giraffe.
So that last one is so it's one or the other. It's not
Yes,
both. It's not like both simultaneously.
no, it'll be one or the other depending on the context of the problem.
Okay.
So they might ask you, like what proportion of the population have cell phones instead of landlines. So they'll ask you for the proportion, or they say, what is the probability of randomly choosing a household with that it only has has no landline. So they'll ask you one or the other, what's the probability or what proportion of the population? The math is going to be the same for both. Good question. Thank you, Justin. All right. So we have giraffes. The weight of giraffes are approximately normally distributed with the mean of 2,200 pounds and a standard deviation of about 200 pounds. We're going to draw a normal curve. We're going to label stuff. We're going to shade to the left of 2,100 pounds so that we can see which part of the normal curve we're dealing with. And then we're going to interpret this result. I feel like I should back up and talk slower. It's only 6 o'clock. I have one more slide. You guys are going to get out of here super early tonight. All right. So here's my graph right here. We have the normal curve. Here's my mean right here. This at 2,200, that's the mean. And we have shaded to the left. Whoa. Here's the 2,100, as I can't draw a nice straight line. Here's 2,100. I'll make it work. Approximately right there is 2,100, and we shaded to the left. So the area of this is going to give me what I'm looking for. So that area right there is the proportion of giraffes whose weight is less than 2,100 pounds. It is this right here. So about 30.85% of all giraffes weigh less than 2,100 pounds. So if I randomly selected a giraffe, the probability that it weighs less than 2,100 pounds would be about 0.3085. Those two differences make sense. So one is about how much of the population, and the other is the probability of choosing one with that characteristic. So with the population, I'm not actually taking a sample. With the probability, I'm wanting to know what's the probability that I choose one and it has that characteristic. Questions?
Wait, how did you get the number 0.3085? Was there a formula?
We're going to learn that on Thursday. This is just the interpretation. We're learning the interpretation first. On Thursday, we're going to do all the math. That's the 7.2 stuff. You will get that on Thursday. And it's all calculator functions. So I'm going to, before I close this out, because it's only 6 o'clock, I am going to pop into the final project sheet. Let me get back to there. I'm going to pop into the final project sheet because I think this could be valuable. Because we still have a next step. We have our data. So I am down here, project assignment folder. This right here gives me that sheet. So to start off, so today was the project proposal, and this is just you just giving me ideas. And I don't care if you give me 3, 4 ideas, whatever. I will respond to all of them. So that's due tonight, and it's just very simple. So what it says here is draft an informal proposal describing the question you want to answer with your project and what data you're planning to collect to answer the question. And it's just says, just feel free to give me a sentence or two. Just type it in the show work box. And it's super informal. Even if you really have no clue, just give me some things you're interested in and some ideas of variables, even if you're not sure how to compare them. I want to know what you're interested in. I want to know a couple of variable ideas, and I can try to go from there. Try not to be super vague if possible, but if that's all you've got, if you say, I am really interested in nursing and I want to know if maybe there's a connection between marriage and blood pressure. I don't know. I'm making stuff up, but that right there would be perfectly fine because I'd be like, okay, there's 2 variables I can work with. So I want to kind of have an idea of what your variables might be and then what you're interested in. So the data set is the next thing you're going to be turning in. So notice that it's not just the data set. It won't let me make this bigger. Notice that it does say to collect your data set. So you need 50 variables or 50 data values, 2 variables, 50 data points each. So if I was doing this, maybe blood pressure, number of hours that people work, I know that you blood pressure is two numbers, but just go with me. One of my variables would be number of hours they work. The other one would be blood pressure. I would lay that out. 50 people, their 50 people's number of hours they work, 50 people's blood pressure, and I would that would be my two variables. And I'd need all 50 of those. I want the raw data. I do not want you to do anything with it. Just give me the raw data. And then that is your 10, that's 10 of the points. Lay it out in Excel. That's 10 points. You get 5 points each, or 5 points for you need to talk to me about how was your data obtained? What were the sampling methods? What was the source? Maybe you went to NFL.com and you just looked at player stats. You would tell me I went to NFL.com and I looked at the player stats and that's what I found. Possible bias. So maybe those were old player stats and that's not what their actual current is. Maybe I can't make a prediction because people are injured this year. If there's any kind of bias at all, and there's really probably not with statistics on an NFL.com. I'm just riffing here. But for example, if you polled your friends on social media, you are going to have a limited number of people. So if you're a 20 something person, you're probably going to have a higher number of 20 somethings in your social media circle. So that could be a possible bias. So just talk about stuff like that. How did you collect your data? What are possible biases? And it's not super strict here. I just want an idea of how you got where your numbers came from. Next, why do you find it interesting? Finally, I want to know that. On your all your labs before that, I didn't care if you found your data interesting. Just find your data, call it good, and on the labs. But here, I want to know why it's interesting to you. You get 5 points for that. Make sure when you are doing your turning in your data set that you do these last two. I can't tell you how many times people do not do these last two. And this is not something that you can go back and reclaim those points. When you submit it, you submit it. So make sure you're doing all three of these things. List your data, description of how it was obtained, and statement of why you find it interesting. So as far as I'm going to go, you will have a written report and a presentation. Those are a little ways off, and I don't want you to worry about those right now. So these are the two things I want you to worry about. Any questions on the final project before I turn off the recording?
So for the proposal, you said it would be okay if we had like a couple of ideas, we could kind of pitch those to you and then you can kind of give us feedback on what you think would work better.
Yes.
Okay,
Yeah.
perfect.
Because I don't expect you to have anything fully fleshed out right now. Some people do sometimes, but I'm expecting it to be super informal.
Okay, great. Thank you.
You're welcome.
I have a question.
Yes.
That example that you posted, it was one of the examples was somebody did a comparison of Tesla versus like owning a Toyota
That was
gas.
a fun one. I love that one. Yes.
Right. So like on as far as those that first picking 50 data points,
Mm-hmm.
what types of data points did they use? Or is that, can you tell from that looking at their, right?
This is it. Let me see here. Okay, I know that they have gas prices
Uh-huh.
and okay, so it was gas prices and electric prices.
Mm,
So here's
okay.
the gas prices in all 50 states, because the state itself is not a data value, but it's a good way to break up your data. If you're not sure how to get 50 data values, find something that you can find in all 50 states. So they have the gas prices in 50 states, and then they have how much electricity costs in all 50 states. And that's what they were comparing for um,
Right,
the cars. And I mean, he compared a lot of other things. He did so much here.
right.
I'm sure that you can guess this one probably got some extra credit here. I think this one did. I'll have to look back, but this might not have been the one that got extra credit. I now that
It,
I'm looking
it
at it.
looks pretty thorough.
It is really thorough. I know that if he didn't get extra credit, he definitely scored really high on it. And even though I don't feel like I'm giving anything away by saying it was a he, but But this was, I mean, this was a really good one. And yeah, that one, that one's one of my favorites. Tesla's one of my favorites. Super Bowl was one of my favorites. Oh, look, this one's hidden. I need to unhide that one. Any other ones hidden? No. I don't know why that one was hidden. That was weird. Okay. Yeah. These are just fun. Super fun. And yeah, I believe it was gas prices, and I bet things would look much different right now. Even, something similar. And I don't even know if necessarily, I mean, I don't know if Tesla is the best one. Wonder if you could even compare, um, like I know that China has some really interesting um, electric cars and things that their electric cars can do. It would almost be, I don't know how you would compare them and what that would look like.
Like how far they go on a charge, and
Yeah,
then
but
how much
I don't
that
know how
costs.
you'd get 50 data values on that though. That's the thing is, yeah, that's what we have to think about is how am I going to get 50 data values? But, there's some interesting things there. I don't know. Yeah, I don't even know. I do love I love things like the electric cars. See, this guy was really into cars, and he actually had an electric car. I don't know if it was a Tesla, but he had an electric car and he was really interested to see, am I really saving money? And I'm going to tell you a fun fact on the Super Bowl one. I really hate the Broncos. And sorry if you guys love the Broncos, but he purposely made this Broncos colors because he knew I hated the Broncos. So the Super Bowl one, he was kind of poking fun at me, and that's why it's blue and orange. So anyway, any other questions? All right, I'm going to turn off the recording.